Elena, you can hear me okay, and hopefully you can see the slides. I will look up at the chat periodically. It's just you and Evan, so it's just the two of you. I feel very grateful to both of you for coming to make this worthwhile. So hopefully this will be a useful thing for you too. It's basically about a game that I've been working on at MIT for the last couple of years. So um, basic overview of the presentation. I will give you some context for this project. We'll go over the learning objectives. It's an educational game. And I'll talk a bit about the timeline. We can do a demonstration. So, all right. So it is a part of a $5 million 3-year grant from the Office of Naval Research. And actually, back when Trump was president, the US government identified, I think, 12 or 14 areas of sort of emerging technology that the US government wanted to support to educate the US workforce. Integrated photonics was one of those areas. MIT put in a grant in combination with a couple of other institutions. And
So I
nice.
Plans list.
Okay, thank you. And we got the grant. And so I knew nothing about integrated photonics prior to starting on this project, but basically, integrated photonics are fiber optic technology. So basically, shooting light through various materials, but at microchip scale. That's what integrated photonics are. So fiber optics plus microchips, that's integrated photonics. And a lot of the microchips that we had manufactured previously used basically pushing electrons through metal like miniature wires. And integrated photonics are much better than that in many ways. Mainly heat. It just generates much less heat to shine light through instead of push electrons through. And speed. You just get a lot higher bandwidth. So that's what we're trying to teach people about, lots of different ways that you can apply that technology to different features in real life. So we're in year 3 right now. It's scheduled to end in October 2022. And our target audience for this are basically community college students or aspiring technicians so that they can be familiar with this technology that it exists. So the grant covers a bunch of online courses and simulations and also 4 games. So these games are sort of a small piece of the overall puzzle that should be considered in context, right? We're not intending to teach everything just through this one game, but it's part of a whole package of educational material. All right, so I already talked about basically what integrated photonics are, and let me talk a little bit about the game itself. So I've designed 2 games, this sensing game, that's one application for integrated photonics, and then a LiDAR game, which is in development right now. And then Rick Eberhardt, who's also at MIT, designed 2 others on data centers and wireless communication. We are using an external game development studio called Firehose Games, and they're based in Boston. And we have roughly a $250K budget per game. And that buys us a full-time programmer and a 40% time artist for about 22 weeks. So
I was gonna say, the 250K sounds like a lot, and then you burn it through very quickly.
yeah, so they're reasonable scope. I don't think it's like AAA, but it's also not nothing. We can do plenty of interesting things with that.
Way more than a game jam, for example.
Way more than a game jam. Yes, yes. No, it's a real game. So just to give you a sense of all the project members, I was on it as the game designer and sort of half producer. We had the programmer and artist of Firehose Games. We had a internal programmer who worked on the prototype and also is doing a little bit of sort of final bug fixing after the Firehose team moved on. And then we had a whole slew of subject matter experts who knew a lot more than me about integrated photonics. And I basically had science lessons with them for quite a few months to learn more about integrated photonics and specifically the sensing application. So All right, so what were our learning objectives to get out of this game that was really designed to teach about sensing? How to use integrated photonics for to sense things in the environment. So number one thing is we want to have a player who plays this game increase their engagement with the matching online course material. So the professor who is teaching the online course says, here's all the course content, and by the way, here's this game that you can play. We want those to work in tandem and in sync. That was like number one most important thing. Secondarily, we want them to gain some familiarity with integrated photonics in sensing. So integrated photonics is the general technology. How do you apply that technology? You could apply it to data centers. You could apply it to wireless communication. You could apply it to LiDAR, and you can apply it to sensing. So we're focused in this game on sensing. Okay, we want, so integrated photonics, you're building this microchip, and on the microchip, there are different sort of ways that you can build it and construct it. And we want them to actually learn about some of the ways that you're building this microchip. So some examples of those you'll see later. And then when you're building it, there's some thoughtful trade-offs that you might consider. Do I want a microchip that's like really, really good at detecting even trace amounts of whatever material I want to detect in the environment? Or do I want something that's like super reliable? Like if it's going up on a spaceship, then I need it to really be super reliable. If I'm building in some like massive pipeline, maybe I don't care exactly how small it is, it can be bigger. If I'm going to mass produce them, I need to make sure the cost is really low, these sorts of trade-offs. So we're trying to introduce players to that sort of idea. All right, so those are our 4 learning objectives for this game.
So those are like your 4 main actionable variables, like in the game design would be size, weight, power, cost?
Yeah, you'll see. So it's hard to know exactly how much detail to go into for students who might not already be like deeply familiar with this. We try and it's a level-based game, and by the end, we hope that players who are playing the most advanced levels will be able to make some of those decisions. And we surface some of the cost and size and sort of accuracy variables to them in the way that they can construct the circuit. All right, here's a rough timeline for the project. We started initial concepts in April 2020. I'm sure nothing was going on then. We began digital prototyping in October 2020. And then the professional team, so that's Firehose, began in November 2020. We hit alpha about 4 months later in March, beta a month later, and then they basically rolled off in June last year. And we got, like 95, 98% done. But there were a few like minor bugs that we still need to fix. And so that's when Trevor, who's at MIT, also worked a little more on it. And we sort of absolutely hit final base. I mean, still there are always little things, but it's basically done as of January this year. So that was the rough timeline for this project. And I talked earlier about sort of we got 1 programmer and 40% time of an artist. I was half-time on this project, being both game designer and producer. And then we had about a quarter time from a subject matter expert across all of the subject matter experts. And then a little bit of contract time for audio and QA.
What are the different subject matter experts you need to consult?
There was one main one who is designing the online course, and she knew the most about integrated photonics, in particular the sensing application. But there were other sort of details, like she focused mostly on chemical sensing, like if you wanted to detect like methane in the environment. But then there were other people who were doing like testing if you wanted to theorize like detecting COVID or something, right? You get a drop of blood, you put it on this microchip, you shine light through it, and then it can tell you right then, is there COVID or not? Like that's more of a biological sensing environment. And so we talked to sort of people who specialized in that. So it was primarily one. Her name is Anna. Okay. So I just thought it might be useful to talk a little bit about our process as we built this game. So we had a continuous build system via cloud build, and we used Unity. And basically, at any time, anybody on the team checked in anything, either a programmer checked in new code, I checked in some new design, tuned some files, or the artist checked in new stuff, we would get an automated build. It was integrated with Slack, and so anybody on the team at any point could be playing the most current build. And that's, I always recommend that. I think that's it's a good system. It takes a little while to get set up, but it worked pretty well. We had weekly meetings. I had weekly team meetings to keep the artist and programmer on track. And then I also, in addition to that, had weekly science meetings with the subject matter experts so I could learn more about the science. And then we used a bunch of tools to maintain communication remotely. Everybody was remote because it was during COVID, and so we were never meeting in person. We used Trello for task management. We used Slack for general communication. Then I had a game design document that I used to maintain various design features.
Like I haven't developed a game in person in 4 or 5 years.
Right.
At this point, this is all of our development environment.
Yes. Yeah. Do you use different tools or
You got Trello, Slack, and Google Docs.
Same as you?
Yeah, absolutely. For the reasons of orientation, of threading, making sure that the different tasks are addressed, and then for longer text or spreadsheets, which are our friend, are the Google Docs and
Nice.
nothing fancy, but those are the ones that we can rely on.
Nice.
And I'm also interested in your Unity cloud build setup that we talk about a little bit later.
Yeah, I'd be happy to. And I'm not sure if you heard, but I haven't agreed with everything that I said.
Yes, yeah.
Same systems.
Yeah, that's right.
So I won't click on this, but this is what the original prototype looked like. So I don't know if anybody remembers Train Yard, but it was a mobile game a while back where you basically drew train tracks, and that's sort of what's happening here. You sort of can click and place these parts basically that the light flows through as you're building the circuit. And then you can test it, and there are a variety of sort of goals that you're going to get as you proceed. So this is what the digital prototype looked like. We had obviously no art on this, as it's just all programmer art, and we had, I don't remember exactly how long this was. I think this was about 4 weeks, and it was a great help to me in identifying some of the design challenges or things that were a little unclear. So. I definitely recommend digital prototyping if you have the luxury of getting to do that. So I think for this demonstration, the easiest thing is going to be for me to show my, I'm just going to show a video and then talk over it. So this is a video that I recorded previously. Can you see this? Elena, it's not showing up yet. I wonder, let's pause and then resume. I wonder if that's going to work. Let's stop sharing. And then let me share again and see if you see this. Share it. Okay, great. So this is a video. This is what the game looks like. I'm playing this in the Unity app basically, and I will talk over myself. So it's level based. We have a bunch of levels to choose from, and we sort of break it up into introduction, which are the basic UI stuff, and then chemical sensing and biological sensing. So this screen is what the player will see when they first come to a level. There's this little introduction area at the top that gives them pretty direct instructions about what their goals are for the level, and then a little more detail from the science that should match with what they're learning in the course, and then the objectives that they need to accomplish to be able to pass this level. So that's what they're seeing on this intro screen, and then it gets minimized into the sort of detail bullet points up top. I should have just talked over myself talking because I probably just said what I just said. So this first level is really designed to get the player familiar with the UI. You have a little toolkit on the bottom where you can choose from the components. This is the first level, so there's only a single component that the player can choose from, and that's the spiral. So they can click on the spiral, they can add it to the circuit, and then they'll be able to test the circuit and see how the circuit functions. So this is just a basic UI test. I'm hoping that my past self will click on this spiral in a moment, and you'll get to see it. All right, so yeah, so there we go. I'm putting this spiral. It would have been easier if I had a live demo, but I don't have Unity on this machine.
It's all good.
All right.
This is funnier.
It is a little funny. So, all right. So I can, if I place a spiral, I'll be able to show you that. The other thing, oh, right. I'm talking about the size of the chip. So you had asked about the swap C trade-offs. Right now, you may notice that there's like this grayed out area and then a dark gray area. At the moment I add the spiral, it actually made the chip a little bit bigger and the chip cost went up. And so we're not like actively teaching the player about this right now in this first level, but we are sort of exposing this information to the player so that the curious player will be able to learn about it. And I just noted that basically that microchip is being fed in from a laser on one side and then photodetectors on the other side as the light passes through the microchip, and they can zoom out and basically see that if they want to. Do they need to do that on level 1? No. But we're sort of giving them the chance to learn about it from the beginning. So the major component costs for building this in actuality are the lasers and the photodetectors. The chip itself maybe isn't that significant of a contributor. And now the basic idea of the way sensing works is that the light comes in right here, and then you split the light into the top and bottom. And then you have one spiral that's not exposed to the environment and another spiral that is exposed to the environment. So you might have seen me, I went down to expose, and then I clicked up here to expose it. And you'll see that now I'm testing it, the light is going through, and it's simulating the fact that because there's methane in the environment, you get a lot less power, a lot less light going through the top than the bottom, because as it gets exposed to the methane in the environment, it gets absorbed. The methane absorbs some of the light. That's basically the idea of this technology for sensing applications, is that different materials have different wavelengths of light that they absorb. And if you know that those wavelengths, then you can properly like shoot the laser light through at those wavelengths, and then if it gets absorbed, you know that you've detected methane. And that's the sort of the key idea of sensing. And that's what we're teaching in this game.
So this is a microcontrol experiment sort of situation all enacted with light.
Yeah.
How does the spiral split the light? Maybe.
Oh yeah, no, yeah, it's fair to be confused about that. So the spiral is not splitting it. What's happening is, we'll see on the next level that I go to.
Oh yeah, okay, I see the overview.
So this is a bit of, I guess I'm talking about resizing. So right here, if you look right here, this is a separate part that is a splitter. So the player, like, this is an early level in the game, and so we're sort of putting the splitter on the board for the player already. But normally they would have like a spiral down here, and a splitter, and an edge connector, and a bend, and a straight piece, and then they would place the splitter as they wanted. So this is the thing that's splitting the light, and then it goes through spirals separately. And then you might see here the 3240 nanometers. That is the specific wavelength of light that methane, at which methane absorbs light. And if I had chosen a different wavelength, then it would just pass right through this spiral. It wouldn't get absorbed at all, and we would see these numbers being the same. So we sort of had to build a whole model of the way that light actually interacts with materials to be able to build this game. So I think here I'm showing an example of actually choosing the laser and getting to select the photodetectors and building the whole circuit. And now you can see down here, okay, there are a bunch of different tools that you can components that you can pick from as you build the circuit. So
Is there some creativity to building?
yeah, exactly. Exactly. Yeah, you can build it however you want. And there are some reasons why you might choose one over the other. The main thing is you want it to fit into the smallest area as possible. That's really what you're trying to do. Um, because you could make the spirals go anywhere and you could make the bends go anywhere, but to save cost you really want it to be as small as possible. So that's a quick sample of what the game is. There are a bunch of different levels, there are a bunch of different components, there are different objectives, there are different things that you might try and detect, not just methane but other things as well. And there are some other sort of fun objectives like a timed level where you're trying to do it very quickly, or levels where we put sort of things in a way that you have to try and get around just for fun. That sort of thing. That's all possible. So that's sort of where it is now. We have not had a chance to test it with the online course, but that is going to be happening soon, and that should be hopefully a lot of fun. And then we'll get more information. We actually have a bunch of learning scientists on the grant overall, and we should be able to basically get them to analyze. Okay, did this actually help or not? So hopefully it will, and then I'll have more to share when we do. Okay, I have a few extra slides, and I think we have a little bit of time, so I can show that. Some lessons learned. I just thought it might be nice to conclude with that. Okay, so I think number one, and maybe this is pretty obvious, but I think that the fact that we had subject matter experts on the team from the very beginning helped us a lot in making a game that is really meaningfully connected to the subject that they were trying to teach. This is a game in service of a course, and by having them working on the game from the beginning, we had confidence that the sort of the levels that we were developing matched the coursework that they were doing. So I think that's number one. And number two thing is, obviously in time of COVID, this is even more relevant, but we had some situation where one of the programmers had to roll off the team, and because we had the luxury of a backup programmer, we were still able to deliver the game. And it's not always possible. No problem. It's not always possible, but I think that was successful in this case. And then I would say the last lesson learned, this was more a reminder to myself, but I guess to other designers, this was a game based on real science. And at the beginning of the project, I had ballpark science numbers from the subject matter expert that were easily within an order of magnitude. Like they weren't off by more than one order of magnitude, but they weren't exactly right. And I knew that, and they knew that, and we were all like, it's fine, it's going to be no problem. And then basically, as we and we built the systems that I could just go in and modify those numbers, like it was super easy to change them. But I just didn't actually have the actual science and the actual data. And so at the very end, near the very end of the project, I was like, okay, subject matter expert, give me the numbers. And they gave me the numbers, and it messed up my level design because I had set level design thresholds at certain numbers, and they weren't off by a lot. Like the numbers that I ended up with were like off by a factor of 2, maybe, but it was enough to throw off several of my levels that I ended up having to rework. And so, in a situation where I could have asked for the science data sooner, really no reason not to have done that. Maybe I will save you some rework if you remember that on your projects. So, that's it. Thanks so much. Yeah, thank you. So I'm happy to take some questions. Elena, I don't know if you have questions. If you want to type them, feel free to type. One other person joined us. I'm sorry, I don't know your name, but Mike, welcome. I'm sorry you missed most of the project and most of the presentation, but no worries.
is basically a Navy project related to creating sensors, right? So they're and specifically using optic microchips to sense.
Yeah, to detect things in the environment. Exactly right.
Example we have there is rapid, but it could, you know, one thing that Ira suggested is you know, biological matters with the COVID could also be created to the sensing environment once they have isolated in a specific capacity.
But the idea is to educate fundamentals about photonics,
Yes.
not about sensing.
Right. So integrated photonics is an emerging technology that exists kind of in research labs. Some has been commercialized, but there are a bunch of different ways of using integrated photonics as a technology. One of them is sensing. Another, for instance, it's used a bunch in LiDAR. It's used a bunch in data centers. It's used a bunch in wireless communication. So one of them is sensing.
I've worked with our photonics folks before.
Oh, nice.
Long ago. Is just to be sure, when you're talking about workforce, you're kind of talking about people who service these photonic stuff as opposed to the research on
Correct.
fundamental physics and
Right. So this is to familiarize them with the existence of this technology. They're going to be
not
working.
necessarily why and how it works.
Yeah, I don't know to what extent, why and how. I think if you have a technician who's working on some technology, like a piece of technology, and they show up to try and fix it, I think having some sense of how and why it works is valuable. Like, does the cable repair guy know anything about the way cable works? Like, maybe not.
The guy that's putting the fibers together knows what he's doing.
Right.
At least has a skill set of a surgeon.
Right.
Right. And the Navy thinks so. I mean, that's why they think
I think it begs the question, do they need it, and are they better at being a technician if they have it?
Right. Yeah, I don't know. I think that the assumption is yes. The assumption is.
Does it invite that? I'm sorry, I missed. I'm
Oh, no.
in my individual presentation.
No, it's fine.
Party dilettante or.
Yeah, no, I mean, we haven't deployed it with technicians yet. This is basically in an educational environment where somebody is signing up for an online course.
A community college.
Yeah, exactly. Or a technician who's already working in the field and then is going to do some exactly.
Yeah.
That sort of thing.
But yes, I've wrestled in the past with other things, like people work in chemical production labs, how much do they know about the fundamental chemistry to run equipment?
Correct.
Some kind of simulation
Right.
inside. Is that what this is doing?
Yes, absolutely. Yes. This is exactly a simulation of what's happening in this.
Paths to deeper understanding of something, can they approach that?
Yeah, that's certainly the idea. So it's a
Yeah, but how do you achieve it?
right. And I would say we don't know yet because it's not done yet. The grant will end in October. The idea is this game is one part of a bigger educational suite of materials that they have access to. So there are online simulations, there are online courses, and there are games.
All right, how is this playful?
Yeah, so yeah, no problem. No problem.
I mean, the cool thing is you can build any number of types of circuits, and you just need to have the basic components that you need in order. And one of the main game-like challenges is to constrain the size of your chip because it's going to directly affect the cost of the chip. And so you're trying to, I guess, integrate all of the sensor connections that are needed in the smallest possible space.
But there's no aspect of this being citizen science where, like, where if they put something together and it works better, then that would come back to you, or you would analyze that.
You're right. It's not citizen science. So this.
Teaching game, right?
Yeah, exactly. It's a teaching game where we have confidence. We know some of the ways that these circuits should be put together.
Gotcha.
We want them to understand it should be put together that way.
Some of my weird things, that kind of thing, being creative is educational.
Oh, for sure.
To do that.
Yeah,
That
so,
becomes playful.
yeah, that's right. So I'll show you. This is roughly what the game looks like. So,
Say, start throwing stuff together in the circuit,
right.
my mind goes someplace it probably shouldn't.
No, no,
That
that's,
often happens in my mind.
It's all good.
yeah, oh, you can't see that. I'll stop, let me stop sharing. It doesn't, share, share this. So here's the,
Oh, there it is. Okay.
here's what the circuit looks like. So when you first, there are a bunch of levels, um, there are a bunch of levels, and then you go through sort of these intro levels and the more advanced levels. The intro level, you just have, you know, we have built out the circuit for you. We're teaching you the basic UI. You have to make sure that you can add a spiral and expose it to the environment.
Are there goals though, or
Yeah.
quests?
Yeah,
that you go through?
Exactly. Yeah, I mean, it's level-based goals. So each level has a specific goal, and
After tests, move on.
Yeah.
exactly.
Yeah, you see where it says test and.
But I don't get new stuff.
You do. So right now,
And capabilities in the simulator.
yeah, more stuff for sure. Yeah.
Because you get the spiral, you get like the little splitter, and you're, yeah, you can build the circuit and you
Right.
know.
What's the value of me having more stuff? Get more head knowledge from MIT or play more and have more.
You can build different things.
autonomy?
Yeah, you can build different things.
Good.
More, yeah. And I think that you know, in any sort of situation where you're,
Like mine.
yes, where you're doing a model like this, you want to model reality so that the student can learn about the way things work. But at the same time, you want to give them the freedom to experiment and make mistakes and do wrong things.
Yeah.
Uh,
Explodes.
exactly.
Make it overheat.
Exactly. Yeah. Yeah, there you go. That's a good intro to what the game is. I have 5 more minutes. Maybe it's worth showing the LiDAR game. It's a much more well, you'll see it.
And there are metrics on the circuit somewhere. Am I seeing like
Yeah, exactly. Yep.
some instruments of it?
Yes.
When you click test, like that's it.
Yeah. Yeah. Let me
It's
see.
like running the simulation.
Right. So if I go, yeah, you'll see it. There are a variety of tests that are, I don't know exactly when. Okay, so here I'm pressing test. I test it with methane, and you'll see the light pass through the system and then sort of propagate through the system. Then it splits into the top and bottom. And then at the top, the light is absorbed by methane in the environment because we've chosen a wavelength of light at which methane absorbs light. So,
See the methane coming off.
exactly. Yeah, and so you could, exactly. And it's a significant thing. I mean, it's a significant thing for climate change.
Stop it.
That is,
Here to discuss the merits of cow plot.
We are gonna do that.
all right. So let me see if I can show maybe this guy and go to this guy. Okay, so this is a game that's very much under development. We're really not, it looks way more polished than it actually is. This is,
Well done then.
this, well, it sometimes gives the wrong impression. So,
The intention of looking better than it is.
yeah, maybe. So this is a game designed to teach the player about LiDAR. And LiDAR basically is shooting light, infrared light, out into the environment, having it come back to the sensor, and based on that, being able to detect how far away something is.
Great.
That's the overall,
Underwater drone, it's great for you.
exactly. And so this is particularly relevant in self-driving cars. We've chosen jet ski just to avoid issues of running into people and to have a little more playful environment.
It's still aim jet skis of people.
Yeah, that's true, but at least in our game, there aren't people in the water. So, right, there's like a buoy and things like that.
Yeah.
So the basic idea of this game, like many infinite runners, is to just get as far as you can, and the player has some control. They can crash pretty easily, and one of the things that we want to get across to them, and again, this I'm feel like maybe the learning objectives aren't quite as forefront in this one as the other one, but we have one of the ways that you can upgrade the jet ski is to have a sensor on it. Right now, it doesn't have any sensor, but you can upgrade the sensor, and then it could get sort of a normal camera. And once it has a camera, then it could.
That's all for now.
It was.
But not people.
No,
Just
no,
saying.
no. It's fine. You can crash into a dolphin on a parachute. That's no problem.
You know they're intelligent creatures for one.
Yeah, that's true. That's true. But you know.
They may even be self-aware.
Oh, fuel.
Okay, so I'll show you the upgrade. So let me I'll buy a camera, and then you'll see now I can get some power-ups and things like that. I have missions that I'm trying to complete.
I earned those.
You can buy them with your currency. Yeah. By playing.
By playing this
Yep.
only, or one of the other?
It's self-contained. It's just this. So basically, this is giving you in the bottom right a sort of a picture-in-picture view of what the jet ski is seeing.
Yeah.
And you'll notice that there's quite a lot of exactly, and it sort of does have sensing abilities. Right now, it's the best that you can upgrade to is a camera, but you can go beyond that once we get to implementing it, where you can get LiDAR. And the benefit of LiDAR, particularly in this sort of environment, is if something is misty, if the environment is misty and you can't sort of see very far in front of you with your eyes or with a camera, exactly, LiDAR can let you do that. LiDAR lets you sort of see through mist.
This totally increases by becoming foggier.
Yeah. And the real idea of why we have mist in there is to demonstrate why does it even matter to have LiDAR? Why don't you just use a camera? And the answer is, well, if you have LiDAR, then you can see even in mist. Because
It's a lovely game, man.
it's true. It's true. Anyway, I just thought it'd be fun to show off that little prototype. We're still working on it, but
I think it'd be nice to have it bag some of my head knowledge about circuits and photonics, maybe deeper concepts of photonics
yeah,
towards my acquisition of the LiDAR.
yeah,
It's much more playful.
that's right. That's a great suggestion. Yeah, it'd be really nice to have sort of cross pollinate from the different sort of subjects.
Intentionally and integrated.
It is. That's true.
Maybe even things each person will then contribute.
Yeah.